In this chapter, we will be exploring the calculus of trigonometry. In this lesson, we will be looking at applications of trigonometry.
All right, hi everybody. So we're going to start looking at some applications of trig derivatives and just jump right in here. So the question is, what is the minimum area of a triangle that can be drawn such that a rectangle measuring 6 by 2 is inscribed in it? Well, the thing to do with this one really, the first thing we got to do is take a look at it. So here's our triangle. Okay, and we're going to inscribe in this, or we're going to draw inside it a rectangle that is supposed to measure, let's say 6 units by, what was it say? I think it said 2 units. Yeah. So this right here would be 2 units right there. Okay. Now we're going to come up with the area of this triangle. We're looking for the minimum area of this triangle. So one of the things that we're going to do here is we'll drop an altitude straight through. Okay. And I think you can tell right away that this little distance here is going to be 3. Now, to come up with the area that the triangle, here, bear in mind that the area of a triangle is 1/2 base times height. So 1/2 base times height. Okay, well, what's my base? Well, my base is going to be 6 units plus a bit here. And now we've drawn this to be symmetric about that middle line there, and that's a bit of a choice on our part here, but that's okay. So we're going to call this x, which means that this would be x over here. So the base of this triangle is going to be 6 plus 2x. Now the height will be 2 units, okay, because this middle line right here will be 2 units, plus this additional little bit up here, so it'll be 2 plus y. So 1/2 6 plus 2x multiplied by 2 plus y. Now, I can distribute this 1/2 through this first binomial here, okay? And I will get 3 plus x multiplied by 2 plus y. Now, and bear in mind, I can do that because sometimes people get confused and they think that 1/2 has to get distributed to both of these, but multiplication does not distribute over multiplication. It distributes over addition. Okay, so I don't distribute the 1/2 to both of these. I've multiplied those first 2 factors together. When I multiply these together, I will have multiplied the 1/2 by everything there. So don't feel that you have to distribute that. Please don't do that. But now when we multiply these 2 binomials together, we'll get 6 plus 3y plus 2x plus xy. And you could probably see this as clearly as I can. There's too many variables here. That's kind of a pain in the butt here. So what I'm going to do is I'm going to introduce another variable here. This is where the trig is going to pop in. I'm going to call this angle here theta. And you can probably see right away that if that's true, based on the fact that that's a rectangle, this would be our transversal across the 2 parallel lines, there's going to be theta and theta right there. So I'm going to introduce this variable theta to help me make this question a fair bit easier. And in fact, it does make this a lot easier here. So from this bottom triangle right here, I can see that the tangent of theta is going to equal 2 over x. And so by a little bit of cross multiplication there, I can see that x is going to equal 2 over the tangent of theta. And by that same argument, I can go up here, I see that, whoops, oh shoot. I can see that the tangent of theta will equal y over 3. And then again, by a little bit of cross multiplication, I see that 3 times the tangent of theta will equal y. Okay, now, with that in mind, I can make some substitutions into my area calculation here, into my area formula. So let's just move down here. I want to be able to see that. But my area, okay, will now be 6 plus 3 multiplied by y, so 3 tangent of theta, plus 2 multiplied by 2 over the tangent of theta, plus, okay, now this is going to be 2 over the tangent of theta, there's my x, multiplied by y, which will be 3 times the tangent of theta. Now, okay, granted, that is a little ugly, and I get that. but it's all at least in terms of one variable. And so now I can clean things up a little bit. This is going to be 6 plus 9 tan theta plus 4 over the tangent of theta. And notice what happens here. Notice the tangents cancel each other out here. So I'm just left with 6 here. So putting this together here, I'm going to get 12 plus 9 multiplied by the tangent of theta plus 4 divided by the tangent of theta. Okay, so now at least it's in terms of one variable. So that is a bit easier. How do I then solve for this? To figure out what the minimum area is? Well, what I do is I take the derivative. Okay, so now we're going to take the derivative of area with respect to just the single variable now, theta. Well, the derivative of 12, 0, goes away. That's wonderful. The derivative of 9 tangent theta will be 9 secant squared theta. And then bear in mind that what this is the same as cosecant here, or sorry, cotangent I should say. When you take the derivative of that, that is going to be negative for what is that? That's cosecant squared theta. Oh, sorry, that's right, cosecant squared theta. For a brief moment there, I wanted to make that out to be a little bit more than it is, so I was going to write down a slightly different derivative there, but that's it. Okay, because this is the same as for cotangent of theta, the derivative is going to be negative for cosecant squared theta. Okay, now let's simplify this a little bit here. It's probably going to be a little bit easier to see if I write it out as 9 over cosine squared theta minus 4 over the sine squared of theta. Our common denominator will just be the product of those two. So this will end up being 9 sine squared theta minus 4 cosine squared theta over the product cosine squared theta sine squared theta. Okay. It would be beautiful. Oh, and that's a little bit hard to see. Maybe I'll expand that out. Let me just write that out like this. So it'll be like this. 9 sine squared theta minus 4 cosine squared theta all over cosine squared theta sine squared theta. A little bit easier to read when it's nice and big like that. Now, it would be nice if I could just do the sine squared, cosine squared, and say, hey, equal to 1, but I can't. So what I'm going to do here is I'm going to use an identity to get rid of the sine squared there. Let's make that 1 minus the cosine squared of theta. Okay, minus 4 cosine squared theta all over the product of those two. Cos squared theta, sine squared theta. I'll multiply that through, and when I do, okay, I'm going to get 9 times 1, and then it'll be negative 9 cosine squared theta minus 4 cosine squared theta, so minus 13 cosine squared theta all over the product of cosine squared theta and sine squared theta. Okay, so there we go. So now we're going to be looking for the critical numbers here. So we're looking for where the numerator is 0 or the denominator is 0. Now, the denominator will go to 0 if theta is equal to 0, or theta is equal to pi over 2, or if theta is equal to 0. Okay, sine squared will go to 0 at 0, cosine squared will go to 0 at pi over 2. So this is going to be undefined at at theta, we should say, theta equal to pi over 2 or 0. But now let's go up to our scenario here. Take a look at that. Just think about what that would mean for theta here. Pi over 2 and 0. Neither one of those work. In this particular scenario right here, it has to be the case that theta is some value in between those two. It doesn't make sense in this scenario for it to be either one of those endpoints, because you don't get a triangle in those scenarios here. So where the denominator goes to 0 isn't going to make a difference. So now it's where the numerator goes to 0. So let's talk about that. I got to look at where 9 minus 13 cosine squared is equal to 0. So let's take a look. So that would mean, well, we'll just write it out like this. 9 minus 13 multiplied by the cosine squared of theta. I got to figure out where that's equal to 0. Okay, so I would bring over the 9, make it negative over there, divide by that negative 13. So this would be the cosine squared of theta is going to equal 9 over 13. So cosine of theta, we'll just take the square root, could be positive or negative. Okay, could be positive or negative root 9 over 13, which will be positive or negative 3 over root 13. Now, again, because I'm looking at angles between 0 and pi over 2, really, I'm looking for scenarios here where the cosine of theta is equal to the positive 3 over root 13, not the negative. The negative would put us into quadrant 2 or quadrant 3 for that matter, and neither one of those quadrants makes any sense for the value of theta. So theta here, if I do an inverse cosine of this, okay, theta is going to equal the inverse cosine of positive 3 over root 13. And so we're going to get approximately equal to 0.59 radians. Okay, when I plug that in. Now, that tells me where I've got a maximum or a minimum here, but I don't know which one it is. So what I got to do is I got to investigate. So I'm just going to take a quick look at my number line here. I know that 0 makes sense as my minimum, pi over 2 makes sense as my maximum, and so somewhere in here is going to be my 0.59. Okay? And if I choose a radian value between 0 and 0.59, if I plug that into my derivative here, okay, you will find that that the value at the end there, and I mean I could do that for you, but just take my word for it. If you plug in, for example, 0.5 into this, you are going to get a negative value. And if you plug a value between 0.59 and pi over 2, so if you plugged in like 0.6 even, you would find that this interval here becomes positive. So what we know here is that the function is decreasing, okay, on this interval and increasing on this interval, which makes this 0.59 therefore. Okay, so therefore theta approximately equal to 0.59 corresponds to a minimum. Okay, corresponds to a min. Minimum what? Well, because it was area that we took the derivative of, it's going to correspond to a minimum area here. So now my area, I'll come over here. So therefore my area is going to be 12 plus 9. Now we go back to my expression here. 9 tangent of theta plus, remember I had 4 over the tangent of theta. But now I can figure something else about this here. Just take a look. If I know, and watch this, I'm gonna be a little bit lazy here. If I know that the cosine of my angle, okay, if the cosine of my angle here is positive 3 over root 13, let's just go down here and talk about that. Okay? If I've got a triangle here, and here's my theta, and I know that my angle here, my cosine here is going to be 3 root 13. Well, let's just do a little bit of math here. Okay, root 13 squared is 13. 3 squared is 9. 13 minus 9 is 4, and the square root of 4 is 2. So just using the Pythagorean theorem, I get that the opposite side is 2, and so therefore I know that the tangent of theta is going to equal 2/3. I see, I love being able to do this because then I don't need to go to the calculator. I already know that the tangent of theta here, in this case, that corresponds to the scenario where we get a minimum area, is going to be 12 plus 9 multiplied by 2/3 plus 4 divided by 2/3. And when all's said and done, that gives me an area for the triangle of 24 units squared, whatever those units happen to be. Okay. So here's just one example of applying trigonometry, and a great example because you see right away that by putting a theta in here, I take this kind of messy expression with the 3 variables, area, the y coordinate here, the x coordinate here, and basically just make it a comparison between area and this one variable theta. Okay, now here's another one. So the light at the top of a lighthouse is situated 4 kilometers off a straight shore, rotates at 5 revolutions per minute. How fast does the beam sweep across the shore when the angle between the beam and the shore is 50 degrees? Okay, once again, we got to take a quick look at the geometry of the situation. So here's our lighthouse. Here's our straight shore. So we know that the lighthouse is 4 kilometers off the shore here, and it's rotating around. Okay, so let's say it's going like this, and it's doing that at 5 revolutions per minute. Okay, so it's rotating here. The beam shoots out, okay, and hits a point on the shore here. Let's call this angle here theta. That's what's changing. That is the angle that's changing, and we know that d theta by dt. Now let's think about it. That lighthouse rotates. It does a full 2 pi radians, okay, 5 times in a minute. So it does 5 2 pi's per minute. Okay? Does 5 2 pi's per minute. So basically, what we can say here is this is 10 pi radians, per minute. Okay, now we are looking for the rate at which this beam shoots across the shore here. So let's just call this distance here x. And so what we're looking for here in this context, or this question I should say, is dx by dt. I'd like to know what that is. Now, based on the units that I'm given right now here, I am likely to find this in kilometers per minute. And by the way, I'm totally okay with that. Kilometers per minute, okay, because those are my units here, those are my units there. And then if the question needed me to convert it to some other units here, I would happily do so. But right now, I have a sense of where this is going to go here. Now, I'm interested in how fast the beam is sweeping across the shore, so that dx by dt, and I'm interested in it at the instant that beam makes an angle of 50 degrees right here. Okay, now, because that's between the beam and the shore. Okay, that's awesome. That's great, except that that's not theta. I'm giving a very specific angle, but that's not theta. This is theta. But it shouldn't take much to realize that if the instant that this is 50 degrees, that this theta right here is going to equal 40 degrees. Okay, because those are what we call complementary angles. Okay, so let's take a look at what our scenario is going to look like here. I want dx by dt. So I want a relationship between x and theta. Now, because this is the opposite side, that means I'm either going to use sine or I'm going to use tangent. Okay, cosine makes no sense here. I have not been given any information about the hypotenuse of this triangle, but I know that this distance right here, okay, is always going to be 4. And I'm pretty lazy. I like a scenario here where I've got a constant. So actually it looks like I'm going to use tangent here. So the tangent of theta is going to equal x, the opposite, over 4, the adjacent. Okay? I am looking for dx by dt. So actually I'm going to, even before I get into it, I'm going to solve, I'm going to bring that 4 up, make this 4 tangent of theta. So now, dx by dt, which is what I'm looking for here, is going to be 4, the derivative of tangent, okay, secant squared theta, and because theta changes with respect to time, so not only do I take the derivative of the function acting on theta, but I got to take the derivative of theta as well. So d theta by dt. And I'm okay with that because I already know what d theta by dt is. What I don't have right off the bat is I don't know what theta is. Oh wait, yes I do. 40 degrees. Now I'm going to do something a little weird here, just because it'll work regardless here. Normally when we do calculations in calculus with angles here, we are in radians. I am, however, going to do 4, and I'm going to do my secant here. I'm going to do the secant of 40 degrees, and then I'm going to multiply by d theta by dt, which in this case will be 10 pi per minute, but just 10 pi. Okay, now I'm going to leave that as 40 degrees in that function right there. And let me explain why I'm going to do that. The reason that I can get away with that without converting this into radians is because I'm going to make sure my calculator is in degree mode. Whether I take the secant of this angle in radians or I take it in degrees, the result will be the same ratio. Okay? The secant acting on that angle, it's the size of the angle that measures, not the units that it's being measured in. Now, this, however, when I talk about d theta by dt, that has got to be in radians. Okay? When the angle is now being talked about as separate from the trig ratios here, then I got to be a little bit more careful about that. So now, I'm actually just going to plug this all into my calculator here. So 4 secant of 40 degrees, I've got to make sure that's squared, and then I'm going to multiply by 10 pi. And when I do that, I get 214, so this is approximately 214 point, let's say 14 kilometers per minute. And there you go. That's how you'd handle a problem like that. So just be aware, mostly with these lighthouse or these beacon problems, just be aware that of where that angle is typically that's the focal point of the problem here. And when they give you the angle down here, again, that's information here that you need to get this angle. Don't just use that 50 degrees. That wasn't the angle specifically that we needed. And additionally, when you're choosing your trig functions, always remember to look for that constant that's in there and pick a trig function that utilizes both the variable that you're looking for, in this case the dx by dt, and the constant that's in the expression. Makes things a lot easier. Okay, one more application. Two sides of a triangle measure 14 centimeters and 16 centimeters. The angle between them increases at pi over 12, and there's no units there, so I recognize that as radians per second. How fast is the area increasing when the angle is pi over 2? Okay, I want to make sure that we've gone over a question like this, mostly because when I've seen this given, when I give this out to my own students here, I will frequently see people make an interesting choice when they draw this, okay? A lot of times what I'll see people do is their instinct is immediately to do this, okay, and make this, let's say 14, here's your 16, and then they start looking for this angle right here, this is your theta, and they're coming up with the area of it, and actually, sorry, I should be a little bit more, actually that's not what they would do. Let me show you a little bit better here. What they would do is they would draw that out flat. So I'm trying to be consistent with the lines that I made here, but they would draw it out flat. They would just label this as 14 and 16. Now to come up with the area, they then draw this altitude here and try to come up with an expression for the area. But the problem with that is these two are two different lengths. And so when you do that, this and this aren't necessarily going to be the same. That altitude does not necessarily cut this in half. So this is a very awkward way to do this. I would just assume don't do that. Don't do that. What I would do, or at least my advice with this, is use one of those sides as your base. Let's make it the 16. And then here's my 14, and then just connect them. And there's my angle in between. And so now, when I drop that altitude, okay, and I'm going to use that to come up with the area of my triangle. Well, now I know my base is 16. I drew it that way. When the angle changes, okay, the altitude is going to change, but it's going to change in relation to the change of that theta there. So if I pick, for example, h, let h be the height or the altitude of that triangle, okay, now bear in mind the 16 is not actually a side in that right angle triangle, but the 14 is. And so I know that the sine of theta will equal h over 14, or in other words, 14 sine of theta is equal to h. Okay, so now I can come over here and let's come up with an expression for the area of that triangle. It will be 1/2 base times height. 1/2 16 multiplied by 14 sine of theta. Okay, so now, well, let's just make this easy here. Half of 16, well, that's easy. That's just going to be 8 multiplied by 14 sine of theta. And so, putting that all together, that is going to be 112 sine of theta. Okay, now let's take the derivative. Okay, because that's what we're trying to do. I'm trying to find how fast is the area increasing when the angle is pi over 2. Okay, so d theta by dt is exactly what I'm looking for. That is going to equal 112 cosine of theta d theta by dt. Now, when I plug in all my bits of information here, I know that this is going to be 112. I've got the cosine of pi over 2, and I know that d theta by dt is increasing by pi over 12. And when I calculate that all out, I get 0. I get 0 here. That's a really bizarre sort of a result to get. But actually, that makes perfect sense. Let's just talk about what's going on here real quick here, because this is something that you're very likely to stumble upon this coming at it from a different direction, where you might be asked for the maximum or a minimum area here, where you'll take the derivative and set it equal to 0. Here, I'm asking you to find the area at a very specific spot here. Watch what happens. So here's my 16. So as this angle gets larger, okay, as this angle gets larger, whoops, that's probably not the best way to do it here, but anyway, the area of this triangle gets larger until it's vertical, until that's 90 degrees. Then bear in mind that this side length doesn't change. As soon as it starts to come down this way, as soon as this angle crosses over and becomes larger than 90 degrees, now all of a sudden the altitude starts to drop. So here, think of it like this. As this side here, as this side rotates up, the base of my triangle is always 16, but the altitude's getting larger and larger and larger until you get to here, and then as soon as you pass by 90, the altitude starts to get smaller and smaller again. And so what has happened here is the area has increased. In other words, this is an interval where the derivative would be positive. Once we're past 90 degrees or pi over 2 radians, now we're into an interval where the area is getting smaller. And so, yeah, at that exact moment that angle is pi over 2, I expect the rate of change of area to actually become 0. It does make perfect sense. Okay, now here's another word problem here that we're going to use trig with. But you should recognize this. You've probably done this one before without using trigonometry. I just want you to see how trig actually takes this problem and in my opinion, makes this a little bit easier. So what are the dimensions of the largest rectangle that can be inscribed in a semicircle with a radius of 10? Okay, so what we've got here is we've got this semicircle. Okay, and I'm just going to drop this thing on the coordinate plane like this. And I'm going to do it like this because this is how you would have approached this before. So here's your x, here's your y. Okay, the equation of that semicircle would be x squared plus y squared is equal to the radius squared, which in this case, when you do that, it's going to be 100. And then you would find the coordinates of this point right here, and you'd come up with the area of this thing. But actually, I want to show you another way of doing it. I'm going to draw a line from the center to that corner right there. Now I know, because I know that the radius is 10 centimeters, I know that that length right there is going to be 10. Now in this particular expression here, okay, I'm going to let this variable right here be x, and I'm going to let this value right here be y, just like we did before. That's no different. But now I'm going to introduce this other angle here, theta. So now, instead of using x squared and y squared and whatnot, and x and y I should say, I'm actually going to use theta here. Now x, or maybe I should write it like this, the cosine of theta will equal x over 10, meaning that x is going to be 10 multiplied by the cosine of theta. Just like the sine of theta would be equal to y over 10, or 10 multiplied by the sine of theta is going to equal y. Now, I want to come up with an expression for the area of that rectangle. Well, the area of that rectangle is going to be clearly 2x's, because of symmetry, multiplied by y. Which I would do a substitution here. So that's going to be 2 multiplied by 10 cosine of theta multiplied by 10 sine of theta. Okay, so now instead of having the two variables in there, I've got just the one variable, but this time it's theta. Now, previously what I would have done is I would have taken this expression and solved for x or y and substituted it in, but then I'm dealing with a radical in there, and it's a little bit messy here. Watch what happens. This is just wonderful. So 10 times 10 is going to give me 100. And I know you're thinking, well, wait a minute, there's a 2 there. Yeah, I'm going to move that 2 over, and I'm going to get 2 sine theta cosine theta. Now, you should recognize that as an identity. And so this is going to become 100 multiplied by the sine of 2 theta. Now, not only have I got area in terms of a single variable, I've only got it in terms of a single function of theta. That's amazing. And so now I can take the derivative, and the derivative will be 100 multiplied by, well, the derivative of sine is cosine, of 2 theta, multiplied by the derivative of the argument here, which is just going to get me 2. So in other words, I'm going to get 200 cosine of 2 theta. What I'm interested in is where this derivative goes to 0, because remember, there's no d theta by dt or anything out here, simply because I'm taking the derivative now with respect to a change in theta. So now I'm going to set this equal to 0. In that case right now, I'm just divide, and I'll get 0 is equal to the cosine of 2 theta. And now think about that. In order for the cosine to spit out a 0, I know that the argument must be equal to pi over 2. And when I solve for theta, I will get pi over 4. That's the angle that makes this, gives us the maximum area here. So now this is so easy. 2x is the base, and that's going to be 20 cosine of theta. And so 20 multiplied by the cosine of pi over 4, well, that's going to be 20 multiplied by, what is that, root 2 over 2, which is just going to be 10 root 2. That's going to be the length of my rectangle. Y is the width of my rectangle, and that is just going to be 10 sine of theta. So 10 multiplied by the sine of 45, or sine of pi over 4, 10 multiplied by root 2 over 2, or 5 root 2. So my length will be 10 root 2, my width will be 5 root 2. I think that's a fair bit easier. Now, and additionally, if I wanted to know what the maximum area was, and this actually gets even better, because watch this. If I want to get the maximum area, I know that theta has got to be equal to pi over 4. Well, 2 times pi over 4 is pi over 2. The sine of pi over 2 is just 1, so my maximum area is just that 100, just that coefficient right there. It works out so nicely. Okay, everybody, let's take one more problem here. What is the maximum length of a ladder of negligible width that can be navigated around a corner from a hallway 3 meters wide to a hallway 4 meters wide? Now, we got to include this negligible width bit here. Turns out if you include a width to it, the question becomes substantially more difficult. In fact, so much more difficult that you probably need a computer really to crank through the calculations there. But a situation like this is actually pretty straightforward. So let's just draw what this looks like. So here's my hallway that's 3 meters wide, and then we're going to navigate around a corner that's 4 meters wide. So it's really this across this little corner right here that's the issue. I'm going to create these triangles right here. Oops, can't see that bottom one. So this is going to be 3 meters wide. This will be 4 meters wide. And then just like we've done with the last few questions, what we're going to do is introduce theta. And theta is going to go right there. And those will be the exact same values because these two triangles will be proportional to one another. Now, we're looking for the longest ladder that we can navigate this corner with. But we've got two different triangles here. So I'm going to let this be x and I'm going to let this be y. And so my ladder, the length of my ladder is going to be x plus y. This triangle right here, when I look at what information that I'm given, I have no information about this side right here. So really I've got that the sine of theta is going to equal 3 over x. So x will equal, well, if I bring that over, I would divide by sine. So actually I can rewrite that as 3 cosecant theta. This triangle right here, if I look at what I'm given, I've got the cosine of theta is going to equal 4 over y. So when I solve for y here, bring the y up, bring the cosine down, it's actually going to be 4 secant theta. So altogether, the length of my ladder here, x plus y, is going to be 3 cosecant theta plus 4 secant theta. Now, this is wonderful though, even though we're dealing with functions that are maybe not our most commonly used ones, but at least it's all in terms of one variable. So now I can take the derivative L primed, and when I take the derivative here, that's going to be negative 3 cosecant theta cotangent theta plus 4 secant theta tangent theta. Okay, well now all of a sudden I have got a lot more trig functions there than I was expecting, or that I was working with before. So this looks a little bit gross right at this moment right here. But remember what I'm doing. I'm looking for the maximum. So I'm going to set this equal to 0. So negative 3 cosecant theta cotangent theta plus 4 secant theta tangent, secant theta tangent theta. I'm going to bring this over to the other side. And when I bring this over to the other side, I'm going to do one other thing. I'm going to rewrite everything in terms of sine and cosine. And you'll see why in just a second here. This isn't always the best way to approach these problems. But for right now, it might help clarify a relationship that's kind of hiding here. So this is going to be 3 over sine theta. That's that cosecant. And then this will be cosine of theta over the sine of theta, equal to 4 over the cosine of theta, that's that secant, sine of theta over the cosine of theta. There's my tangent there. Well, now look at this. I've got the two sines here, a sine up there, cosine up here, two cosines down here. I'm actually going to bring this 4 down. I'm going to divide that on both sides. I'm going to multiply the two sines up and the one cosine down. This is going to be sine cubed of theta over the cosine cubed of theta. Well, that is substantially simpler. In fact, I can go even one step further. This is 3/4. This is going to equal the tangent cubed of theta. Well, now that's just brilliant. That is absolutely brilliant. So this is going to occur, okay, this will be true when I take the cube root. So now all of a sudden tangent of theta will equal the cube root of 3 over 4. Now, this answer here is only going to make sense. Now, if this is in the first quadrant. Now, the other quadrant where tangent is positive is going to be out in the third quadrant, and it makes no sense for that angle theta to be larger than pi. So when I take and find theta, that is going to be the inverse tangent of the cube root of 3 over 4 okay? And when I plug that in, when I get that value right there, and I don't actually need to get that. I just need to know that that's what I'm going to do. But if I take that answer right there and plug that in, I'll kind of just draw this out. If I take this answer, whatever I get at my calculator, and plug it in to this expression right here, that will give me the length that I'm looking for, and it turns out this is going to be approximately 9.9 meters. Just a hair under 10 meters is the longest ladder that I can navigate that corner with. Now, I have kind of quickly here assumed that what I did find here was a maximum. You have to forgive me for that. I didn't want this to go a whole bunch longer than what it is right now, this video. Anyway, I hope that helps, gives you some clarity.